Alright, here's the first new thing we're going to look at for Chapter 8. We're going to talk about ionic bonding and bond polarity and electronegativity. So I'll start here with 8.2, which is ionic bonding. Okay, I'm going to look at how ionic bonds form. So the principal reason that ionic compounds are stable is your attraction between ions of unlike charges. This attraction draws the ions together and will release energy, which causes the ions to form a solid array, or what we call a lattice. So when we look at these crystal lattices, and we're going to call lattice energy. So this whole array here of positive and negative sodium ions and chlorine ions are your crystal lattices. Okay. Well, when you put a bond together, that is exothermic. You release energy every time you try and put something together. Remember, we talked about last year that things are more stable when they are together. So since you have a lower energy, so if I have my Na ions and my chlorine ions, when they are apart, they're really high energy. They don't want to be that way. They have lots of energy moving all around. Then when they bond together to a positive and negative, now they are set. They have this nice distance with this positive negative pole, and they have a more stable and lower energy. Things like to be more stable and to have this lower energy. So then when we look at something called lattice energy is the amount of energy that is required to break the lattice or the bonds. That would then be endothermic. And that means that in endo, you have to put energy in. These are going to be positive numbers normally. And you see in the chart there, up above, that these are all positive numbers because you're putting energy in. It requires energy. These are positive values. We're going to look a little bit closer at these lattice energy numbers. We're going to look at radiuses. Okay, so I have all these positive, negative lattices now that I want to break apart. I want to break apart this sodium chlorine from another sodium chlorine, and also try and break apart between the sodium chlorides. So I'm going to look at the radius between the two, whether they're closer together or further apart. Well, let's say we look at a large radius, and we're thinking about how easy or not easy that would be to break. Well, if these two are very far apart, so say that now these are positive and negative that are actually bonded together. So I've got a bond here, okay, they're fairly far apart as opposed to this one. So if I want to try and break apart one lattice here and another lattice, it's going to be a lot easier to break these two apart because they're just so much further apart. Positive and negative are not as close as these two positives and negatives. So if you have a large radius, that's going to be a very low lattice energy. They're very easy to break. So the one down here, which is Cs and I, cesium and iodine, well, if you look on your periodic table, cesium and iodine are fairly big elements. They lie in the 5th and 6th row. So the larger your radius, the lower your lattice energy and the easier to break. Be careful to not confuse lattice energy with ionization energy. The other thing you can take into account here is not just the radius itself, but then how the charge plays into that radius. So let's look at this magnesium chloride compared to this sodium chloride. Now, magnesium has a charge of 2+. It's in the second group there, wants to lose 2. Sodium is in the first group, wants to lose 1. Magnesium's lattice energy with chlorine is huge compared to sodium's lattice energy here. So the charge also plays a part. The higher your charge, the usually then smaller the atom's going to be, so the higher the lattice energy. Alright, what I want you to do next is look at the practice problem and arrange the following ionic compounds in order of increasing lattice energy. And I don't want you to look at the chart, so you should be able to figure it out based on your charge and the radius. Okay, your order should be CSI, NAF, and CaO. The reason being, if you're looking at the CaO, you've got a 2+ and a 2-, which is a higher charge than either one of these, which are 1+ and 1-. If you look at CSI compared to NaF, CS has the larger radius. So you've got more energy levels here in CSI, so that makes it a lot larger than its counterpart with the same charge. All right, let's go ahead now and we're going to look at bond polarity. We talked about this in the review section with electronegativity. So let's remember that electronegativity is how much a certain atom in a bond wants electrons around it. So taking that different atoms want electrons differently. Some want them a lot around them, others don't want electrons anywhere near them. So when we look at this electronegativity, we're going to look at polarity. And when we talk about something that is polar, remember, okay, that means that you have a positive side and a negative side. That means that your electrons are going to stay more around one atom than another. So there are 3 examples on the back of your second page. Mine are colored, as you can see here. Yours are not. So let's take a look at mine that are colored. All the way on the right, you have LIF. That is an ionic bond. It's still technically polar. It's just so polar that it's ionic. You have a total positive and a total negative side. They don't share at all. Let's look at the one in the middle. You have HF. I have 2 nonmetals, so I have a covalent bond. But notice how fluorine is more red than hydrogen. Fluorine is the negative end, hydrogen is the positive end, but they still share. And then you have the other extreme, which is the nonpolar example, which is F2, which is a F bonded to an F, so they are shared equally. So you've got a nonpolar covalent bond on the left, a covalent bond in the middle that's polar, and on the right, you've got so polar that's your ionic bond. So a true nonpolar covalent bond is going to be between atoms of the same kind. Any other type of bond is going to be at least a little bit polar. So then a polar covalent bond is where my electrons are not shared equally. So let's look at the example. In each case, which bond is more polar? Okay, so we have BCl or CCl. Well, let's look at and figure out which one has the bigger electronegativity difference. Whichever one that is going to be my more polar bond, because that's going to mean one of the atoms in my bond is going to want the electrons more than the other. So it's going to be more polar. And remember, the most electronegative element is fluorine. So the further you get apart on the table, and the closer one gets to fluorine and the further the other one does, the more polar that bond is going to be. So if you look at BCl or CCl, we're comparing carbon and boron. Well, which one is further away from chlorine? Well, boron is further away from chlorine than carbon. So here, my more polar bond is BCl. All right, then look at PF or PCl. Well, which one is further from phosphorus? Because they're both bonded to P. We're looking at then PF. Fluorine is further from phosphorus than chlorine. Plus, fluorine is the most electronegative element on the table, so anything bonded to fluorine is going to be very, very, very polar.